decomposition reaction. Decomposition reactions means there'll be one compound which will break down into simpler substances. But as you know, some compound will not break down on their own. So there has to be some external force applied. And what are the things which we can do? We can either apply heat, electricity, or light. And depending on which one we are doing, it can be given these three names. If we are breaking down some compound or decomposing something with heat, we'll call that reaction as a thermal decomposition reaction. If we are using electricity, we'll call it as electrolytic decomposition. Or if we are breaking it down with light, we can call it as photolytic. So when we are saying it's not like an option. We can't use any of them for all these reactions. It depends on the compound. Like for this example, calcium carbonate, you have to use heat. You can't use electricity for that. You can't use light for this one. It will not work. It has to take heat only. That's why this is an example of a thermal decomposition reaction. Okay. And one quick note, whenever you are trying to break down something with heat, mostly it will be solid. Okay. Most of the examples, what you see is solid breaking down into some other solid and gas. And for electrolytic, all these examples, whatever we saw, all those electrolytes, they have to be liquid. Only then we can make electricity pass through them, right? We can't have solid passing through, electricity passing through solids. Like it will not work. So for electrolytic decomposition, your reactant or the first product which is bigger, which is getting decomposed, will always be liquid. Like in this case, water is liquid. NaCl, that is also in the molten form, liquid form. It breaks down into sodium and chlorine gas. Same thing over here, Al2O3. This is also molten form, aluminum oxide, and we use electricity to get the pure aluminum and oxygen. So remember, these decomposition reactions are important because we have now itself seen that we can get the metals out. Extraction of metals, it is useful. So we will see this in metals and non-metal chapter also later. Some of these reactions will come up in metals and non-metals chapter while extracting some metals. Let's continue after that. So we have seen some examples of compounds with electricity. Now we'll take a couple of examples from photolytic. Okay, that is compounds with light. Electrolytic, then that's photolytic. So I'll just give you some examples straight away. Can anyone tell me what will be the name of this compound, AgCl? I couldn't hear you. Say that again. What is Ag first of all?
Silver, sir.
Silver, yes. Ag is silver.
Silver chloride, sir.
Yes, very good. It's silver chloride. That's good. Silver. Normally this is white in color. Silver chloride, solid. We can use light to decompose it. When you throw light on it, it goes through decomposition reaction and it gives you pure silver. So let's say we have some silver chloride ore. We can purify, get the pure silver using this photolytic decomposition. Gas will be evolved, it will not be there anymore. We'll get the solid silver. Does it look like a good use of this application, good application of this decomposition reaction to We get silver metal from silver chloride. Another example, very similar. It will be same silver, but instead of chloride, have a bromide. Chlorine and bromine, they belong to the same family. We will see that. Chlorine, bromine, iodine. They belong to the same family. So their reactions will be exactly similar. However, the reaction happened with chlorine and silver. Same thing will happen with bromine and silver. Okay. So what would be the name for this one? This compound? Can anyone tell? This compound, what will be the name? Ag is silver. Yes, very good. Silver bromide. It was chloride, so it will be bromide. If I put AgI, it will become silver iodide, chloride, bromide, iodide. Okay. And the color of this silver bromide is pale yellow. So of course I can't write in white color, so I'm using white. Decomposition reactions. See some. So the most important use of this decomposition reaction will be extraction of metals from chloride, bromide, or oxides of metals. Metal chloride like silver chloride, metal bromide like silver bromide. Oxide also just now we saw aluminium oxide, right? So this is an oxide of aluminium, chloride of aluminium, silver, bromide of silver. So from there we can extract the metals. This could be one of the applications and use of this thing. We have seen the examples. All right. So with that, we are done with the decomposition reaction. Anyone has any questions about the two types of chemical reactions we have seen so far?
Sir, so silver oxide is also there?
Silver oxide, yes, oxygen would react with silver also, but silver is a very less reactive metal. It does not react with so many things. Gold, silver, they are very less reactive. So let's see. That is Ag2O. Okay. It's a fine black or dark brown powder. From this also you may extract the silver. Ag2O. Okay. Any other questions? Today we started from this. So this is Now let's get to the third type of chemical reaction. Anyone has a note from that? Can you check and tell me what will be the third type of chemical reaction? Saw the first one as
Displacement.
yes. Very good. First one was combination. Second one was the opposite of combination, that was decomposition. In this decomposition, we saw three types: thermal, electrolytic, and photolytic. And then we are going to the third type, which is displacement. Okay. We're going to talk about this one now. Remember, there are more types after that. So we are on the third one right now. Like always, we'll start with the definition. What would you say that what is displacement reaction? So a reaction in which so let's see some examples of displacement reaction and then it will start making more sense. Okay. So I will write the name. Whoever understands what the name could be, tell me what is this? Cuso4. What do you think the name will be?
Copper sulfate, sir.
Yes, very good. SO4 means sulfate always. Okay. Since this is copper, it will become copper sulfate. Very good. So this is copper sulfate, and the color of this compound is blue. This is a blue solution. This is aqueous. That's why it's a blue solution. Now, this copper sulfate, if it reacts with magnesium, zinc is another metal, right? Copper is one of the metal. Zinc is another metal. So if this reaction takes place, then what happens? Look at the reaction and tell me what do you think happened here? Sulfate was for copper, but zinc, when it reacted, zinc went and took the place of copper and it became zinc sulfate now, and copper got separated. So who displaced what?
Zinc displaced copper.
Yes, very good. In this reaction, zinc has displaced displaced copper. Displacement reaction, when one compound, one element displaces other element. So now tell me if everyone, this displacement reaction makes sense.
Yes, sir.
Yes, sure.
Again, this one is also, let me complete the information about the product also. Reactant, I wrote this copper sulfate is aqueous, zinc is solid, and I told you that copper sulfate is blue solution, it is blue in color. And when it reacts with zinc, it becomes colorless. So zinc sulfate, what you have here, this is colorless compound. Magical, right? If you have something blue, you put some zinc into it, displacement reaction will take place and the blue color compound will become colorless. It's an interesting reaction, right? Blue solution turns colorless. So remember, yeah.
Sir, it is like quite similar if we add turmeric to milk. From white color, it will change to yellowish color.
That's right. But this seems more magical to me. Blue color and zinc, that is also a colorful thing turning colorless. It's very magical to me. Something which has a color and suddenly the color vanishes because of the displacement. Okay. And this statement which I wrote here, which compound displaced what? So the zinc displaced copper, that is also important. Remember this wordings. Displaced what? Zinc displaced copper. And why do you think zinc is also a metal? Copper is also a metal. Why did zinc displace copper? Because copper is more reactive than, sorry, zinc is more reactive than copper. This kind of displacement happens whenever displacement happens. The more reactive metal, whichever is more reactive, will displace the less reactive one. So if zinc is displacing copper, it means that zinc is more reactive. Zinc is the bully, bigger guy, goes and displaces the copper from here. Okay. Let's take more examples. It will be very similar like this only. So another example which is exactly similar, very same. Instead of zinc, we will use some different metal. Cuso4, again aqueous solution. Instead of zinc, let's make it react with magnesium, which is also another metal. Magnesium is also a metal like copper. And what do you think will be the product? Can anyone tell me? Cuso4 reacting with magnesium, what do you think will be the product?
Magnesium sulfate.
Yes, MgSO4, magnesium sulfate. Very good. And another product? Copper.
Copper.
So don't forget that. Copper will also be there. Okay. Okay, I think I'm writing two. And then I'm grabbing space on the right side. So let me write it clearly. MgSO4 plus copper, which is solid. Okay. So these names, should I write it again? No, right? Will be comfortable with the names? Just let me write the color. Again, this is blue. And this one is colorless. MgSO4 is also colorless.
Sir,
Yes, tell me.
sir, like you said that copper sulfate is added to magnesium, then that liquid will convert into magnesium sulfate.
Yes.
Then copper will become crystals.
Yes, it will be released. It will be solid. Magnesium will take the place of copper, and copper, whatever comes out, that will be solid. And it's a red brown color, actually reddish brown color. Okay. Same thing here also. Okay, so we changed blue solution to colorless. Let's use some different metal this time. We tried with zinc, we tried with magnesium. Let's take the same copper sulfate, but with iron this time, and see what happens. So CuSO4. Of course, it is blue in color, and this time we'll take iron. Tell me what will happen. What will be the product? What will be the products?
Fe plus SO4, FeSO4 plus Cu.
Yes, very good. FeSO4, that is iron sulfate, plus copper. Only thing is iron sulfate, the color of iron sulfate is not colorless. It has some color. It is greenish in color. Iron sulfate.
So if we use like the ferrous word instead of iron, sir.
Say that again. Ferrous sulfate.
How do we call? Yes, sir. So if it is iron sulfate, we'll call it as ferrous sulfate, sir.
Yeah, but the names can be different. Names can be used. FeSO4. See, this is iron 2 sulfate, so this will be called ferrous sulfate. Okay, sulfate has a valency of 2. So right now these things you do not understand clearly. I will talk about valencies later. Okay, that time these things will make more sense. Yeah, here I mean to say. So sulfate has a valency of 2. So in this case iron will be called as ferrous. But if the valency of iron is 3 over there, that time it will be called ferric. So depending on what is the valency of iron, like I told you, iron can take dual valencies. Some of the compounds have dual valencies. Depending on what they are reacting with, they can share or lose different number of electrons. That is how their structure is. Same like for iron. We had seen examples that in some places it will be valency will be 2, in some other place valency will be 3. Wherever it is 2, it will be called as ferrous. Wherever the valency is 3, it will be called as ferric. To avoid that ferrous ferric confusion, you can just write it as iron sulfate in simple. Because right now you don't need to bother about the valencies of iron, because that is little complex for 10th standard right now. Okay, so you can simply call it as iron sulfate. If we have time, I'll explain you why the valency of iron is different. Like 2 and 3, both. How can it be possible that both the valencies 2 and 3 are possible for iron? Why it happens? It has to do with the same thing like I've been telling you, SPDF, the way in which electrons get filled up into the orbit and the stability of all those sub shells. It's a complex topic. I probably won't even study that in 11th standard. I don't know. Don't bother too much. Whenever you see ferrous sulfate, just write it as iron sulfate. That's good enough for you. Okay. But But remember, whenever all these colors I'm telling you, these things are very important. Blue solution turning to greenish color. So then you should remember about this particular displacement reaction. Try to recall that. Okay, blue thing changing to green. Okay, there was I studied about a displacement reaction where copper sulfate turned into iron sulfate, and this turned from blue to green. Questions may be asked based on this kind of color combinations. Okay, that is why I'm very specifically writing the colors wherever applicable. Blue solution turning to green. Copper is red brown color. So there can be so many examples of this. Okay. So what I will do is I will leave some space over here, and or maybe I will add some page later. Okay. So I'll add more examples here later. All of them will work in a similar manner. You can make note of all those things, and you can try to remember as many as you can. Okay. After the class, I will add more examples here. So I think this displacement will be more, the idea of this displacement reaction is clear to everyone. More reactive metal goes and displaces the less reactive one. Iron is more reactive than copper. That is why iron took the place of over here.
Sir,
Yes, tell me.
so if we use less reactive metal here, then it will not change the place?
It will not change. Copper will be more reactive, so it will not leave the sulfate. It will not, the bond between copper and sulfate will not be broken. So it will be same thing. Nothing will happen with it. Only because iron is more reactive. So basically it goes and snatches the sulfate from there. Think of it like more powerful, more reactive, and takes the sulfate from there and leaves that copper guy alone.
Sir, sir, if we use Na in place of Fe?
Sodium. Okay, so now,
Yes, sir.
now your question is asking whether sodium is more reactive than copper or not, right?
Yes, sir.
So that reactivity series we will see later in the coming chapters. You do not need to worry about. This is just an extra information which I told you that whenever we are going through this displacement reaction, more reactive element will displace the less reactive. So exact order of those reactivity of those elements, we will see that in later chapters, specifically in the third chapter of chemistry, metals and non-metals. So I don't want to bring that over here right now. Okay, I will show you the order. And if you are interested, you can go to the metals and non-metal chapter. Actually, it will be there in the reactivity or order of reactivity of those elements. It's mentioned here. Okay, since you asked me, let me show you. Okay, the reactivity series. This is your topic. Third chapter, reactivity series. This is what we call it. Which element or which metal is more reactive compared to the other. Now look at this one. And the most reactive will be at the top, least reactive will be at the bottom. So tell me, your question was copper sulfate, and you make it react with sodium. Do you think sodium is more reactive than copper? Look at this and tell me.
Yes, sir.
Yes, it is. Okay. Sodium is high up, very, very high. So potassium, sodium, calcium, magnesium, these are one of the most reactive metals. Least reactive, copper, mercury, silver, and gold. Gold will be the least reactive. That is why we use it for jewelry. Because if something keeps reacting with the surrounding, you would not want to make a jewelry out of it, right? Otherwise, it will react with oxygen or something around, sweat or whatever is there around. And it will make forming some compound. That's why we use gold for jewelry. Okay? But we'll go into the details of these things later. reactivity series when we come to the third chapter. But if you want, you can try to learn this now also. Start learning this so that it will be helpful when we get to the chapter. Try to make the song out of it again. Okay, break it down. Kanaka Magal, Zanfaber, whatever, like that. Make your own song. Try to remember the order of reactivity from top to bottom. Fine. So where were we? I said I'll give more examples of displacement reaction. And then since we have just understood displacement, I want to take up the fourth type, which is double displacement also, because it's very similar. Just an extension of the single displacement, whatever we saw above. Above we saw that one metal going and displacing one guy over here. So double displacement will be just an extension of what we saw above. So again, we will start with the definition. CRT definition. See, this type of chemical reactions I'm not teaching from NCRT. I'm just giving you my examples directly from other books. But I want you people to go through all these things: combination reaction, decomposition reaction, everything from this book over here. And I want you to make sure you understand everything. So we will read this also. As you can see, the same examples, whatever we took, those things are over here. Okay, silver chloride, sunlight breaking it down, silver bromide. Then we took up the displacement reaction, copper sulfate reacting with iron, copper sulfate with zinc, copper chloride with lead. This is one extra example. So I added anyway later. So these examples you can see, these are all displacement reaction or single displacement. Then I'm going to talk about double displacement. Okay. And double displacement is little special because it has one more name. Most of the double displacement reaction, they result in forming precipitate. Okay, so they are also called a precipitation reaction. Whenever some precipitate is formed, double displacement reaction will also be called as precipitation reaction. Okay, fine. So let me just give you the definition quickly. Displacement reaction in which okay. So I'll explain what it means to exchange the ions. Okay, I'll explain that. that, but let me give you example first and it will become very, very easy. Anyone can guess the name? What is the name of this compound? AgNO3?
Silver nitride.
NO3 is nitrate, okay?
Okay.
Silver nitrate. And this one, NaCl, what is the name?
Sodium chloride.
Chloride. Okay. What are the metals here? Can you recognize? What metals do you see here?
Silver and sodium.
Silver is a metal, Ag, and sodium is another metal, Na. So these two are getting displaced. Why displaced? Double displacement is happening. Now Ag will go from here and take the place of the chloride over here alongside with chlorine. And sodium will come and take the place over here with the nitrate. That is why there is a double displacement. Can anyone guess what will be the product? Tell me.
Silver chloride and sodium nitrate.
Yes. It will become AgCl, that is silver chloride, solid, and sodium nitrate, NaNO3. This is aqueous. Okay. And this AgCl, whatever you see, this is a solid as you can see. And all these things are aqueous solution. So whenever this reaction takes place, there will be some amount of solution in which this guy will be a solid alone. So whenever there is a solid inside a liquid, this will form a precipitate. Okay. And this precipitate is of white color. And like I said, whenever precipitate is formed, this will also be called as a precipitation reaction. Okay. So let me give you just, I'll take just one more minute and I'll write down the definition of that precipitation reaction. So whatever insoluble solid you see here, that is what is called precipitate. Okay. So a reaction in which insoluble solid is formed. And like I've been telling you, most of the double displacement reactions will also be precipitation reaction because precipitate is formed here. So this reaction, whatever I gave, is also an example of precipitation reaction. Let's stop here. Anyone has any questions? Let me know.
No, sir.
Make sure you go through the notes. I'll share this PDF today again, like every day.
Sir, precipitates can be in different colors.
Yes, yes, precipitate can be of different colors. So this guy, whatever was formed here, it is white in color. Why do you think it is white? Because it's made of silver chloride. So silver chloride is white. This precipitate is white color. Some other examples may be of different color. I'll give more examples in the next class. That's it, right? Any other questions?
Sir,
Yes, tell me.
so my question is out of this today's, like you taught, it is out of it. Can I ask it still?
Yeah, go ahead, tell me.
So if we mix all the elements from the periodic table, what will happen?
Mix everything. See,
Yes, sir.
when you say that mixing all the elements, no one has done that because that I don't think it's so easy. Not everything reacts with everything. See, when you have studied these 3-4 chapters in science, right? Chapter 1, 2, 3, 4, and 5, and even 6. This chemistry of 10th standard, when you study, right, then you will realize that not everything reacts with everything else. Only metals can form bond with non-metals. So if I just take hydrogen and try to mix it with lithium, they will not react with each other. Sodium will not react with magnesium. Why? Because sodium also wants to give away electrons. Magnesium also wants to give away electrons. So both of them want the same thing. So how can they react with? They can't form bond with it. Actually, they're fighting with each other. Whoever is more reactive will take the place of that other element. They're competing with each other in the reactions. Okay. Same way on the right side where you have non-metals like fluorine, chlorine, bromine, all these, oxygen, sulfur, nitrogen, all carbon, all not carbon, but yeah, all these compounds, again, they try to accept electrons, the ones on the rightmost side, specifically chlorine, bromine, iodine, and oxygen, sulfur, these things. They try to accept electrons. So they will not bond with each other. So there are only specific combinations which are possible. Not everything you cannot, it's not like a khichdi where you mix something and whatever we want we can form. It's not like that. It doesn't work like that. Okay. Right. So I think we are already exceeding the time. So let's stop it here and we'll take up more questions in the next class. All right. See you guys then.